Have you ever wondered why certain objects stick together while others repel each other? This universal observation isn't just a fascinating quirk of nature. It's a fundamental aspect of our physical world, underpinning the very structure of the universe. Today, we're diving into the intriguing science behind these phenomena, exploring the captivating world of electric charge and field. You see, the world around us is teeming with invisible forces. These forces, though unseen, govern the interactions between objects, dictating whether they attract or repel each other. We experience them every day, from the static cling of a balloon to your hair to the way magnets snap together or push apart. But what are these forces? How do they work? And what do they tell us about the nature of the universe? These are the questions that spark our curiosity, driving us to explore, to understand, to learn. In the next few minutes, we'll unravel the mystery of these invisible forces. So, what exactly is this invisible force that causes attraction and repulsion? Enter the realm of electric charge, the fundamental property of matter that brings about this unseen yet powerful force. Electric charge can be thought of as the very essence of particles, the underlying reason behind why they behave the way they do. Now, let's delve a little deeper into electric charge. All matter is made up of atoms, and atoms in turn are composed of protons, neutrons, and electrons. Protons, found in the nucleus of an atom, carry a positive electric charge. Electrons, on the other hand, orbiting the nucleus, carry a negative electric charge. Neutrons, also residing in the nucleus, are neutral, carrying no charge. The strength of an electric charge is measured in a unit called coulombs. But here's what's fascinating. The electric charge isn't just random. It follows a pattern, a rule, if you will. It comes in two types, positive and negative. Now, imagine two positive charges or two negative charges. What do you think will happen if they come close to each other? They repel each other, pushing away in a desperate attempt to maintain distance. This is because like charges repel each other. But what about a positive and a negative charge? Well, they do the exact opposite. They attract each other, drawn together like two pieces of a puzzle. This is because unlike charges attract each other, this dance of attraction and repulsion, this interplay of forces, is what makes electric charge so intriguing. It is this invisible force that holds atoms together, making up the solid matter that we see around us. It's also the force that causes lightning in a thunderstorm, illuminating the sky with the majestic display of nature's power. And that, my friends, is the concept of electric charge in a nutshell. It's not just a scientific term or a chapter in a textbook. It's a fundamental law of nature, a cornerstone of our understanding of the universe. That's the magic of electric charge, an invisible force that governs the interactions between objects. But did you know that not all charges are created equal? Just like the grains of sand on a beach, electric charges too are discrete. They don't come in any random size but are always a multiple of a very specific value. This is what we refer to as the quantization of charge. Let's break it down. The fundamental unit of charge is the charge of an electron or a proton. This charge, which we'll denote as E, is a tiny specific amount. In the world of physics, we find that all other charges are simply multiples of this unit. This could be 2 times E or 3 times E, or even 1,000,000 times E, but never 2.5 times E, or any other non-integer multiple. This means that charge, like matter, comes in discrete quantities. It's a bit like how you can have 1 apple or 2 apples, but not 1.5 apples. A fascinating concept, isn't it? But how do charges know that there is another charge nearby to either attract or repel? Well, let's think about it. Imagine you're in a dark room and you can't see anything, but you can feel a breeze, a slight movement of air. This sensation tells you that somewhere in the room a fan is blowing, even though you can't see it. Similarly, charges can't see each other, but they can feel each other's presence through something we call the electric field. The electric field is a region around a charge within which other charges can feel its effect. It's like a force field that surrounds a charge, extending out into space in all directions. If you place another charge within this field, it will experience a force, either being pushed away or pulled towards the original charge, depending on whether the charges are the same or opposite. Now, the strength of this electric field isn't the same everywhere. It's strongest right next to the charge and weakens as you move further away. If you think about our fan analogy, it's like how the breeze feels stronger the closer you are to the fan and weaker as you move away. The direction of the electric field also depends on the type of charge. For positive charges, the field lines radiate outwards, away from the charge, demonstrating that it will repel other positive charges. For negative charges, the field lines point inwards, towards the charge, indicating that it will attract other positive charges. So, the electric field gives us a way to visualize how charges interact with each other even when they're not in direct contact. It's a bit like understanding how two people can influence each other even when they're not physically close, perhaps through a phone call or a text message. In the world of charges, the electric field is the medium of communication. It carries the message from one charge to another, telling it whether to come closer or to stay away. So the next time you think about charges, remember this invisible force field that surrounds them, guiding their interactions and movements. The electric field is like the charge's personal space, influencing any other charge that enters it. How can we visualize this invisible electric field? That's a question that baffles many, but there's a handy tool to help us out. Electric field lines. Electric field lines, also known as lines of force, are imaginary lines that we use to represent electric fields. They are a visual tool that help us understand and visualize the invisible field created by charged particles. And while they may be imaginary, they are based on very real properties and behaviors of electric fields. So how do we draw these lines? There are a few key rules to keep in mind. First, electric field lines always originate from positive charges and terminate at negative charges. If we're dealing with isolated charges, the lines will extend out to infinity from positive charges and come in from infinity towards negative charges. Second, the density of these lines at any given point represents the strength of the electric field at that point. So, a region with a lot of lines is a region with a strong electric field, and a region with fewer lines has a weaker field. Third, electric field lines never cross each other. Each point in space can have only one direction of the electric field. Hence, if lines were to cross, that would suggest two different directions for the field at a single point, which is not possible. And finally, the direction of the electric field lines at a point gives us the direction of the electric field at that point. If a small positive test charge were placed at that point, it would move in the direction of the field line. In essence, electric field lines are a way to map out the invisible landscape of an electric field. They show us the direction of the field, how strong it is, and where it comes from and goes to. Just like topographical lines on a map, they help us navigate and understand the invisible world of electric fields. So, with electric field lines, we can see the effect of a charge's electric field. So, what have we learned today? We've journeyed through a fascinating realm of invisible forces, a world that exists beyond our immediate senses, but impacts us in every conceivable way. We started with the concept of electric charge, the fundamental property of matter that creates the unseen forces we call electricity. We learned that matter is made up of tiny particles called electrons and protons, each carrying a charge. Protons carry a positive charge, while electrons carry a negative one. And it's the interaction between these charges that leads to the phenomena we know as electricity. We then moved on to the concept of charge quantization. We discovered that charge is not a continuous entity, but instead it comes in discrete packets, a phenomenon known as quantization. The smallest unit of this charge, we learned, is the charge carried by a single electron or proton. All charges we encounter in the universe are simply multiples of this fundamental charge. Next, we delved into the intriguing world of the electric field, the invisible force field that surrounds every charged particle. We learned that this field exerts a force on other charged particles, influencing their motion and behavior. It's this field that allows charges to interact with each other, even when they're not in direct contact. We also explored the concept of electric field lines, a tool that allows us to visualize these invisible electric fields. These lines, we learned, give us a way to understand the direction and strength of the electric field around a charge. They're a powerful tool in our scientific arsenal, helping us make sense of the invisible world of electric fields. And that brings us to the end of our journey through the world of electric charge and field. We've seen that even though these forces are invisible, they're incredibly powerful, shaping our world in ways we can't even imagine. Remember, just because we can't see these forces doesn't mean they aren't incredibly powerful. They're at work all around us, shaping our world in ways we can't even imagine.